aware that you're supposed to have a class at 9. So I hope you have had a nice week. So we continue with the non-steroidal anti-inflammatories. And just a recap to remind ourselves, just one or two things that we studied last time. Of course, we are saying these drugs, which are non-steroidal anti-inflammatories, have a structural similarity with the COX enzymes, and also a structural similarity with arachidonic acid. This is because both these drugs and arachidonic acid compete for the same site, the COX enzyme. And all we are saying, of course, is these drugs should block the conversion of arachidonic acid to the prostaglandins that are responsible for pain, fever, and inflammation. But we did also mention, of course, we have two classes. We'd prefer the selective ones, which go for the COX-2 inducible enzyme. But of course, just for all drugs, first of all, it is continuous development. So you start with the non-selective, and of non-selective, we say they go for both COX-1 and COX-2, and therefore will cause you a lot of toxicity. Because we said then the selective will also go for the COX-2, but we did mention also they will cause you a bit of toxicity because they will also go for the COX-2 constitutive, which is also needed in the body. Then we did mention that when we look at COX-2 and COX-1, in terms of structure, there's a slight structural difference between these two enzymes. And the main difference is that in COX-2, we have valine, and in COX-1, you have isoleucine. Isoleucine is a little bit more bulkier, and I did show you the structure. And because it's a little bit more bulkier, it covers most of the area, unlike the valine, which gives you a pocket. And that pocket is the one which is taken advantage of in development of the selective drugs, in that the selective drugs will have a rigid structure which can go into that pocket, and they will not be able to bind the COX-1 because it does not have that pocket. And of course, also we did say the COX-2 has a much bigger hydrophobic area, and thus, of course, these drugs are made such that they can bind that area appropriately. Because remember, activity comes in when these drugs bind the receptor. They must have good affinity for the receptor, bind the receptor, block that receptor, and therefore arachidonic acid will not have any accessibility. So those are some of the things that we mentioned. And of course, we did mention when we look at that COX enzyme, when you look at the COX enzyme in general, it must be having a cationic center, because both arachidonic acid and the non-steroidal anti-inflammatories do have an acidic center. Most of them, especially the non-selective ones, have a carboxylic group. So we are saying there must be a complementary site on the COX enzyme, and that complementary site is usually a cationic center. And we did talk about the where you can have the guanidinium ion, protonated ammonium ion, giving you a positive center. And that positive center is a center for which the carboxylic acid will bind. Then we did mention that these enzymes also must have a hydrophobic area. And they are having two hydrophobic areas. We have the first hydrophobic area, which we did mention will correspond with the double bond at position 5 and 8. And they also have a second hydrophobic area, which we are saying will correspond with the double bond at position number 11. Of importance to note, we did mention with these two hydrophobic areas are non-coplanar. They are not in the same plane. So therefore, when the drugs are synthesized, there must be groups that are added to make sure that these two hydrophobic areas we are talking about in the drug, the first hydrophobic area and the second hydrophobic area, also show non-coplanarity, because that non-coplanarity is what is needed for these drugs to optimally bind the receptor. And once they optimally bind, then you will get good activity. And of course, also we did mention the toxicity, and we did mention, of course, the toxicity. One reason for the toxicity of these drugs is because of their structure. Most of them are acidic in nature. So because of their acidity, when they get into the stomach, they will not be ionized. The ionized molecule will penetrate the lipid membranes, get into the mucosal cell. Mucosal pH little bit alkaline, a little slightly higher, about 7.4. The acidic drug will be a little bit more ionized, and of course, once it is ionized, it will be trapped inside the cell because, of course, the ionized drugs do not readily penetrate the membrane, and in being trapped, the acidity there now will destroy or will disrupt the membrane, the mucosal membrane, disrupting that membrane, bringing about increased permeability. Of course, active transport of the hydrogen ions back into the GIT, and of course causing a lot of irritation. Of course, we did also say because of that acidity, they can also change the nature. They can change the nature of the mucus. It has less friction, and I mean it has less. It's less viscous. The mucus becomes less viscous, and once it becomes less viscous, it means it does not protect the GIT lining or the stomach lining very well. And again, the acid contents of the stomach can be in direct contact with the stomach walls, again causing direct irritation. So these are some of the areas. So that was one of the toxicity just by their structure. They are acidic in nature, and therefore they bring about increased acidity. The other insult or the other root of toxicity is because of their mode of action, where they are blocking constitutive both COX-2 and constitutive COX-1, and in doing so, they are blocking the synthesis of the prostaglandins that are required for homeostasis, required for cytoprotection, and therefore causing you toxicity. And that indeed, those are the two main ways in which these drugs cause toxicity. And of course, when we do drug development in medicinal chemistry, when we do drug development and discovery and development, you are trying to develop a better molecule, a more superior molecule with much binding, selective binding to the receptor and with minimal toxicity. So that is when, of course, where we'll be looking at the selective non-steroidal anti-inflammatories, which we of course did mention includes the COX-2. Of course, they do, as I have said, they still do have their own toxicities because of blocking the constitutive COX-2. I think that is how far we went, or that is just a recap to remind ourselves of now what we know. And I think now we'll move on, now start looking at the structures. We look first at the general structural requirements. What are the general structural requirements for these drugs? I'm looking at the general structural requirements because they cut across the board. They cut across all the drugs. But for each class, again, we will look at the specific structural requirement for binding, or for that particular compound for binding the receptor. So we can start with point number one on we're looking at the chemical pharmacological properties. I believe that's how far we went. Question up there? Hope that was just a recap of what we had done last time. So we are saying that all are relatively strong organic acids. And of course, we are calling them organic acids, are usually not very strong when you compare them with inorganic acid, but they are relatively strong organic acids because most of them do have the carboxylic group, or of course, some of them can also be the enolics. So with pKa of that, most but not all are carboxylic acids. Like we do have aspirin, we do have ibuprofen, most of them, but the enolics like the piroxicam. The salts can be generated upon treatment. You can generate their salts upon treatment with base, and all of these compounds are extensively ionized at physiological pH. If you look at the handout I gave you, and if you look at mine, I've numbered them the way they are. If you go to page 2, I hope everybody now has a handout. If you go to page 2, I have given an example there. There is a very good example of salicylic acid. You look at salicylic acid. I hope you are together. You can see you can react it with sodium bicarbonate. Sodium bicarbonate is a weak base, and if it can react with a weak base, it basically is a strong organic acid. And if you look at that illustration, you will see it's a carboxylic acid that is first neutralized, or that first neutralized by the sodium bicarbonate to give you the carboxylate ion. The hydroxyl group is a very, very weak acid, and you must react it with a very strong base to give you the ion, the ion of or the negative ion form from the alcohol. So all we are therefore saying is that most of these drugs, that is just a representation of salicylic acid, but that represents almost all the drugs, because we have said almost all these drugs do have a carboxylic acid. All, if not a carboxylic, they do have an acidic center. So that is an example of how these drugs can act. The acidic group is essential for COX inhibitory activity, and we do understand why. Acidic group, the carboxylic group, is when it ionizes, it gives us a negative site. And of course, a carboxylic group or the acidic group is complementary to the acidic group that is found in the arachidonic acid, which binds these enzymes, and definitely it gives us the anionic site. Whereas, of course, these drugs or the enzymes do have a cationic site. The non-steroidal anti-inflammatory differ in their lipophilicities based on their lipophilic character. This is, of course, for all drugs, that their lipophilic character is dependent on their structure. How lipophilic they are is dependent on their structure, and it will depend on the functional groups or the groups that have been attached to these drugs. Again, I want you to look for the structure of diflunisal. Mine is on page 3. Look at the structure of diflunisal and compare the structure of diflunisal with salicylic acid. If you look at diflunisal, you find it has a carboxylic group and it has the hydroxyl group as in salicylic acid, but diflunisal, unlike salicylic acid or acetylsalicylic acid, has a second, you can see it has a second hydrophobic area, and that second hydrophobic area is another phenyl ring, but you can't see that phenyl ring has been substituted with 2 halogens or with 2 fluoro groups. It has been substituted with 2 fluoro groups, and those 2 fluoro groups, as you know, those 2 fluoro groups will increase the lipophilicity. The second phenyl ring also will increase the lipophilicity of diflunisal. So if you compare diflunisal with salicylic acid, you find that diflunisal has much higher lipid solubility because of that difluorophenyl substituent. Diflunisal has a difluorophenyl substituent, increasing the lipid solubility and therefore allowing that drug, although it has a carboxylic group and it has a hydroxyl group, which give it polarity, that increase additional lipophilic or lipid group allows that drug to be able to penetrate the membranes, and therefore diflunisal will have oral activity. And that's all we are saying, that these drugs, their lipophilicity or their lipid character, lipid character is dependent on the substituents, and we see that as we look at the different drugs. The acidic group in these compounds serves a major binding group, that one we've already, ionic binding with plasma proteins. Again, like especially with salicylates, you know, there are very many people who have allergic reactions to salicylates. This is because that carboxylic group, that acidic will bind with albumin, will bind with the proteins found in the plasma, eliciting allergenicity. Thus, all non-steroidal anti-inflammatories are highly bound by plasma proteins, and you can, because they are highly bound by plasma proteins, again, what we expect is that you can get drug interactions. Because once, if you give two drugs, you give a non-steroidal anti-inflammatory, and you give it to another drug, that all, you give them concurrently or concomitantly, and the second drug is also bound to plasma proteins, they will displace each other. And once they displace each other, you will have a higher concentration of the free drug than required for therapeutic activity. And definitely that will lead to toxicity. The acidic group also serves as a major site of metabolism by conjugation. I believe you have done metabolism. Once you have a polar group, like a hydroxyl group, you have a carboxylic group, you have an amino group, you have a sulfhydryl group, like an SH group. Those are polar groups. When a drug has a polar group, it does not undergo phase 1 metabolism because it's already ready to undergo phase 2 metabolism, which is usually conjugation. So we are saying because of that carboxylic group, these drugs can be rapidly conjugated either with glucuronic acid or even with glycine. So they can undergo conjugation with glycine, or conjugation with glucuronic acid. And once they undergo conjugation, they are extremely highly water soluble. They'll be readily excreted from the body. That's a major pathway of clearance for many non-steroidal anti-inflammatories is glucuronidation, or, of course, as I have said, glycine conjugation. That is very general for all of them because of the presence of the of the carboxylic group. But of course, we look at the specific drugs because, of course, the pathway of metabolism also is highly dependent on the structure. So we are saying that is a very, very general structure. There are those which do not agree with this structure, especially the propionic acid derivatives, the acetic acid derivatives, because their carboxylic group is not directly attached to this. But when we look at the phenamates and the salicylates or the carboxylic acids, we do know the carboxylic acid is directly attached. All we are showing here is that you can have that is this is a fast hydrophobic group. That's a fast hydrophobic group. It is attached to the substituent here, whether it's a propionic acid, whether it is an acetic acid, in a planar way. This is directly attached, and these two groups are in the same plane. Then they can be attached through a polar group, like in phonoprofen, or they can be attached directly. So this group can be attached directly, or it can be attached through a polar group, or it can even be fused. So those are different ways you're going to find out. So it can be fused, it can be attached directly, or it can be attached through a polar group. What we want to understand is that we have a second hydrophobic group, and this second hydrophobic group, as we have said, this group and this group are non-coplanar. They are not in the same plane. This group and that group are not in the same plane, and the reason behind that is to allow us to have maximum binding to the receptor. So general structure and property of the NSAID. In general, we have said the NSAID structure consists of an acidic moiety. It can be a carboxylic acid, it can be an amino attached to a planar aromatic functionality. So you have that carboxylic group. This is a planar. This is planar aromatic functionality. It can be aromatic, or it can also be heteroaromatic, but it must be aromatic. So it can be an aryl group, or it can be a heteroaryl group, and that is needed for activity. Some analgesics also contain a polar linking group, which attaches the planar moiety to an additional lipophilic group. So this is like this. Phenoprofen, you have this first planar group attached through a polar group. That can be an oxygen, it can be a carbonyl group, and that second group, as we have already said, with non-coplanarity, which is very important. The center is generally located one carbon atom adjacent to the flat surface, represented by an aromatic or heteroaromatic ring. All we are saying is this. For the salicylates, that point is not well demonstrated, but for the other drugs, even for the phenamates, not well demonstrated. But when we go to from the aryl lacanoic acids, so when all we are saying is that this is our carboxylic group, or our anionic center. When we talk about its anionic center, this oxygen is the one which will be negative. So this is the carbon we are talking about. So we are saying that generally, more often than not, that this carboxylic group is separated from the first planar group by one carbon atom. This is the one carbon atom. This is our anionic, this is our carboxylic group. You can either express it as the carboxylic group or as the anionic center. If you talk about the anionic center, this will be the oxygen, which will be the anionic center. So that time you will say the anionic center is separated from the first planar hydrophobic area with two carbon atoms. Please note, if you talk about the anionic center, because this will be an anionic center by loss of that hydrogen. But if you talk about the carboxylic group, remember the carboxylic group will also take up this carbon. So if you are expressing that difference using the carboxylic group, then you say the separation is with one carbon atom. If you're using the anionic center, it is with two carbon atoms, but that is the same. All we are saying is that it's usually the carboxylic group is separated with one carbon atom. Increase of that size, increase to 2 or 3 carbon atoms as a separator between that carbon and the first planar aromatic center, usually decreases activity or abolishes activity. But we do have an exception to that. We do have the drug we call etodorac. Please look at again your structures. I hope everybody has a printout of what I gave you. If you look at your printout, please look for the compound, the Todorac. If you print, I hope you did, because it would be very careless for you not to have printed. If you have not printed, I hope you have drawn the structure. So if you look at page 9, if you have numbered yours as mine, where you will find Sulida, Kidomethacin, the other compound there you will find is a Todorac. If you look at your Todorac, it's a tricyclic. It has 3 rings all fused together. It has the indoor ring, and then it has the other ring, which is a 6-membered ring, is a dihydropyrene ring. You can write that. You see that ring, which has an oxygen, 6-membered, unsaturation on one side, and an oxygen. That's a dihydropyran ring. And then, of course, it has the indoor ring. Now, if you look at your carboxylic center, and you look at the separator or the archaeo chain that is separating that carboxylic center with the first hydrophobic group, you will see that we have 2 carbon atoms. There is that carbon atom which is at the intersection. So you have the first carbon atom, which is a CH2. You have the quaternary, you have the, not really quaternary because it has an oxygen, but it has it's a carbon which is fully substituted at the middle before you get to a pyro ring. And therefore, unlike what we have said, that separation should usually be with only 1 carbon, we do have an exception of a drug like Todorac. Also look for the drug Ketorolac. Again, I think it is there. Go to page. You look at your, again, if you have numbered yours the same as mine, you look at the page where it starts with tomatin, and its metabolism, then you will see Ketorolac there. If you look at Ketorolac, again, Ketorolac is a drug where what we were talking about, you have the first hydrophobic area separated by a polar group, and then you get the second hydrophobic area, which is a phenyl ring. Now, the first hydrophobic area, you can see it has the pyro group, because that ring there, and the unsaturation, that is a pyro ring. But that pyro ring, you can see it is joined to a dihydropentene ring, cyclopentene ring, dihydrocyclopentene ring. I hope you are together, class. I hope you are all together and you're looking at the drug. You see it has that dihydrocyclopentene ring. It's a cyclopentene ring because it has no heteroatom. It's just a 5-membered cyclic ring, 5-membered cyclic ring with unsaturation. That's why we are calling it cyclopentene. So if you look at where your the carboxylic group is, the carbon of the carboxylic group, whichever way you go, the shortest distance to the first hydrophobic area will be 2 carbon atoms. I hope you can note that. Where you identify where your carboxylic group is, move towards the pyro ring, and you will see the separator. Whichever way you go, whether you go anti-clockwise or clockwise, whichever way you go, the separator is 2 carbon atoms. So again, the Ketorolac and non-classical. We normally call them the non-classical, non-steroidal anti-inflammatories because they do not really obey the rule where we are saying the carboxylic group should be separated with 1 carbon atom for maximum activity. But again, if you look at those 2 structures, you see that their second carbon atom is part of a cyclic ring with retention of activity, and the inclusion of that second carbon atom within a cyclic ring introduces constraint. And once it introduces that constraint, that is what enables that molecule to be able to bind the receptor. It introduces a constraint, and it is like, because of that constraint, it is that molecule or that 2 carbon atom distance still, because it's constrained, it still agrees with the rules, and that drug is able to bind the receptor appropriately. And we will see that when one of the carbons or one of the groups is attached to a cyclic ring, the cyclic ring brings constraint, and we'll mention that severally. When you attach these atoms to a cyclic ring brings constraint and still allows and still gives the correct requirement for binding the receptor. So I had to go there so that you do understand what we are talking about when we talk about that it should be 2 carbon atoms. So now when we read, the center of acidity is generally located 1 adjacent to a flat surface represented by either an aromatic or heteroaromatic ring. I hope that is clear. All I'm saying here by carboxylic, it depends on whether your reference is carboxylic acid or the anionic site, and you can express it in any of them. But of course, you will mention the right number of carbon atoms. The distance between these centers is crucial because increasing this distance to 2 or 3 carbons generally diminishes activity, with the exception, as I have said, of etodorac and ketodorac, which I have said are normally classified as non-classical. They're normally classified as non-classical acetic acid derivatives, whereby we are saying etodorac has a dihydropyran ring and ketodorac has a cyclopentene ring, and their second carbon is part of a cyclic ring with constraint and therefore with maintenance of activity. I hope that is very clear. Derivatives of aryl or heteroaryl acetic acid or propionic acids are most common. So we are saying derivatives of aryl or heteroaryl acetic acids are most common. If you go out into the market, you will get like diclofenac is an aryl derivative. If you get indomethacin, is a heteroaryl derivative. Even propionic acid, the most like ibuprofen, and ibuprofen is a phenol, like the market. We have the ketoprofens. We have we are only saying that when you look at the drugs that are most common in the market, their main structure will either be an aromatic group or a heteroaromatic group, or for whether they are acetic acids or propionic acids. This aromatic system, we have already said, correlates to the double bonds at position 5 and 8 positions of arachidonic acid. Again, very, very important, because there must be structural similarity. There must be structural similarity between these drugs and the arachidonic acid, so that they can be able to bind the COX enzyme, for which these two compounds are competing. Substitution of a methyl group on the carbon atom separating the acid center from the aromatic ring tends to increase anti-inflammatory activity. Like this one now has gotten lost. All we are saying is that if you look at now the propionic acid, if you look at acetic acid derivatives and you convert them to propionic acid derivatives, acetic acid derivatives, once they are converted to propionic acid derivatives by addition of a methyl group, you will find like all the profens, ibuprofen, ketoprofen, naproxen, all of them do have a chiral center. Again, I hope you can understand. Please, you can draw something very simple. Draw your aromatic group. Just draw a benzene ring, kindly. Then draw a carbon atom, and then draw a COH. This second carbon has a CH, and put on that second carbon a CH3. Have we been able to do that, class? Something very simple. I'm only asking you to draw. Just draw something like a benzene ring, because that represents an aryl group. Once, or even just put an R. Just draw an R. Then draw a CH, and from that CH, do a substituent like a CH3 group, and then again on the CH, draw a COH, because that's how the propionic acid derivatives are. Have we all done that, class? Yes or no? Let me see by a show of hands. Have we understood what I'm asking you to do? By a show of hands, class, please. Are we together? Tuko pamoja, class? You have to move together. Yes, very good. So once you have drawn that simple structure, you have your R, a CH attached to a CH3 COH. Everybody can see that middle carbon, which is CH, that is a chiral center. That is a chiral center. R is one substituent. Methyl is another substituent. COH is another substituent. And of course, there is also the hydrogen, which is a fourth substituent. So that is a chiral center. Propionic acid derivatives. For the propionic acid derivatives, you find that the S isomer, out of those, you find for propionic acid derivatives, the S isomer has much higher activity than the R isomer. For propionic acid derivatives, S isomer has more activity than R isomer. For the acetic acid derivatives, because they are acetic acid derivatives, even if you do that substitution, the resultant isomers are equipotent. So like if you look at indomethacin, which is an acetic acid derivative, if you do a substitution at that position, and that's how you are able to differentiate between an acetic acid derivative and a propionic acid derivative. For propionic acid derivatives, when you do a substitution, you get a chiral center, and the S isomer has much higher activity than the R isomer. For acetic acid derivatives, there is the compounds that are produced, both the R and S are actually equipotent. And I believe that space, that the words that are cut there are the same things that all that I'm doing. I'm saying that it will tend to increase activity for propionic acid derivatives. And that's why propionic acid derivatives have much higher activity than acetic acid derivatives. But for an acetic acid derivative, when you put that group there, the resultant compound is two. The resultant isomers are equipotent. In other words, they have equal activity. But for propionic acid derivative, addition of that group to give the propionic acid derivative increases anti-inflammatory activity. And that is why quite a number of the propionic acid derivatives are quite popular, because they have much higher activity than the acetic acid derivatives. Groups larger than methyl decrease activity, but incorporation of this methyl group as part of an cyclic ring system does not drastically affect activity. All we are saying, if you look at ketorolac, etodolac, you find that in those drugs, the group is larger. Actually, if you look at them, most of them will have a CH2 group. The group that is there is larger than the methyl group. But once it is included in a cyclic ring, again, it does not seem to alter the activity drastically. Introduction of methyl group creates a center of chirality. Anti-inflammatory activity is associated with the S-positive enantiomer, of course, as I have said, for the propionic acid derivatives. In those cases, in acid is administered as a racemic mixture, there is in vivo conversion from the R isomer to the biologically active S isomer. Again, I want you to go to page, check which page that is. Yes, go to page 4. We are saying that for most of these drugs, ibuprofen, ketoprofen, you can give them as the racemic mixture. The racemic mixture is where you have a mixture of both the R and S isomer, because it has been discovered that the R isomer can be converted in vivo to the S isomer. But of advantages, the S isomer is not converted to R, and it is the S which has activity. So once you give them as the racemic mixture, as you can see on page 4, you have the R enantiomer. It undergoes, it is acetylated with S coenzyme A, so acetylated with S coenzyme A, and once S coenzyme A is added, it's actually an acylation with S coenzyme A. Once that is added, then it allows for inversion, call it change or inversion of the stereochemistry from R to S. Fortunately, S does not convert to R. So even when you give somebody the R isomer, you are sure it's going to be converted in vivo into the S isomer, and therefore optimize. You will have maximum activity. Again, you can look at page 6. If you look at page 6, on page 6, sorry, it's metabolism. I want to believe I had a page which is showing. In fact, almost all of them, almost all the pages, like if you look at page 6, you will see we have put R ibuprofen being converted to the S ibuprofen, because that is what is active. If you also go to page 7, you will see phenoprofen being converted to S phenoprofen. Check also flabiprofen being converted to S flabiprofen, and that is a position R. Even ketoprofen being converted to the S, and that is because that is what you require for activity. I thought I had also an illustration of ibuprofen. If I don't have it, then that's metabolism. I was hoping I have an illustration of ibuprofen being converted today. I don't have it, but it's okay. But you have seen in almost all the whether it's metabolism, you will have for activity. If you give us a race mixture, it is converted in vivo to the S isomer, because the S isomer is the one which has higher activity. But remember, that is for propionic acid derivative. For acetic acid derivative like indomethacin, the S and R are equipotent. A second area of lipophilicity that is non-compliant with aromatic or heteroaromatic ring generally enhances activity. Yes, 1 minute. Sorry about that small interruption. So we are saying this again, we have discussed, and we are saying that second area is important to enhance. For some of the drugs, it's not there, like for aspirin, it is not there. For acetylsalicylic acid, so there are compounds for which it's not there. But where it is available, like even in diflunisal, in all the other drugs, even in ibuprofen, even in ketoprofen, then there must be non-coplanarity for maximum activity. That group, as you see, it can be an aromatic group, it can even be an alkyl group, it can be fused, as we are going to enhance to state in a minute. This second lipophilic area may correspond to the area of the double bond at position number 11. Again, that we have said enough times. This lipophilic function may consist of aromatic ring, and we have examples: diflunisal, a second aromatic ring; ketoprofen, a second aromatic ring. But it can be a second, even indomethacin, and second aromatic ring, or it can even be an alkyl ring. I mean, so not alkyl ring, an alkyl group. Kindly look at the structure of ibuprofen. Look at the structure of ibuprofen. Ibuprofen, again, my ibuprofen is on page 5. Look at the structure of ibuprofen. Again, you see, this is, of course, a propionic acid derivative. It has the branching. We have, in ibuprofen, we have our first hydrophobic area or aromatic area as the phenyl ring. And then you can now see our second aromatic area or hydrophobic area is an iso, the isopropyl, isobutyl, sorry, 1, 2, 3, 4, an isobutyl group there. So you can see there, you can indeed in ibuprofen, it does not have a second aromatic group. It has an alkyl group. And that sometimes explains why it has much lower activity than the other drugs. So you can see it has an alkyl group with retention of activity. Look at the other structure, which is phenoprofen. The first aromatic group, hydrophobic area, is a phenyl ring, attached through an oxygen, which is our polar group, to our second aromatic area, again, which is a phenyl ring. Caprofen, again, here is fusion. I want you to look at naproxen. Is the best example. If you look at naproxen, you can see the first aromatic ring and the second aromatic ring are fused together. And that's how we are saying that this lipophilic function may consist of an additional aromatic ring or alkyl groups, either attached to or fused with the aromatic centers, with the first aromatic center. So it can be fused, as in naproxen, the very good example. It can be attached through a polar group, like even like in phenoprofen. That group might not be an aromatic group. It can be an alkyl group with retention of activity. So we have 3 alternatives there. It can be an alkyl group. We have an example of ibuprofen. It can be a second aromatic ring attached through a polar group. We have phenoprofen and even ketoprofen. But it can also be fused. The 2 aromatic areas can be fused with each other with retention of activity. And of course, we have an example of naproxen. Next point, all non-selective COX inhibitors possess a center of acidity which can be represented by that. And that we have already said, this center of acidity can be a carboxylic group, an enolic group, a hydroxamic, sulfonamide, or a tetrazole. The acid center is related to the carboxylic acid function of arachidonic acid. The activity of the ester and amide derivatives of carboxylic acid generally is attributed to the metabolic hydrolysis of these products. In other words, if you esterify, if you if you esterify the carboxylic acid, so these are the groups you're talking about, you can have it as a carboxylic group. If you esterify this carboxylic group or you form it into an amide, if it cannot be hydrolyzed in vivo, that non-steroidal anti-inflammatory will not have anti-inflammatory activity. It can have other activity. It's like salicylamide. We find that salicylamide does not have much anti-inflammatory activity. It has analgesic and pyretic activity because it is an amide which is not hydrolyzed. So when you have esterification, that ester must be converted into the free carboxylic ion inside the body. We can also have hydroxamic acid, and we don't have any example of that. We can also have sulfonamides. We don't really have an example of that. We do have the enolics. You see, like this, the way we had done like last time, this bond here can come in, and you have a ketone, and then this comes there. So that now, that will be a carbonyl derivative. So this group here can either exist, can undergo ketoinotautomerism to exist either as a ketone, or it can exist as an alcohol. And because of that ketoinotautomerism, it does give us a little bit, it does display acidity, a slight acidity. And then it can be a tetrazole, but it was a tetrazole is where you have this 5-membered rings, of course, this 5-membered ring, all of it substituted with nitrogen, and this hydrogen can be readily lost. But it was found that substitution with the tetrazole is more expensive and it has no added advantage. So we still also don't have any example of the tetrazole, but we do have very good examples of the enolic acids and of the carboxylic acid derivatives, where we are saying here we have the oxycams, and we have we do have at this particular we have the oxycams, and we do have also the pyrazolidine dione derivatives or pyrazolone derivatives as enolics. Again, this is all that again we have mentioned. They have that carboxylic group, and you can have an example of ibuprofen. So again, when you look at arachidonic acid, this is the area of interest, carboxylic group. That is the other second, what is corresponding with the first aromatic group, and this is corresponding with the second aromatic group that is found within these drugs, or the second, whether aromatic or the second hydrophobic, let us call it the second hydrophobic group. That is the first hydrophobic group. Of course, that carboxylic group is there without failure. So those were the general. I hope you have picked something. Those are the general, just the general SALs which are expected of most, which are expected of the non-steroidal anti-inflammatories. But as I said, we will now be able to look at each group and be specific and discuss now the specific structure requirements, because these drugs do not carry the same structure. We looked at 6 classes. We started with carboxylic acids, acetic acid derivatives, propionic acid derivatives, the phenamides or anthranilides, the pyrazolone, the enolics or the oxycams, and of course we did mention the non-acidic derivatives. So we have a whole 6 classes, and all these classes have differences in their structure, but they obey some certain common rules. Of course, also obeying rules within their own group. So we start with the first group, is the carboxylic acids or the salicylic. Structure and chemistry: kindly draw the structure of acetyl salicylic acid and also draw the structure of salicylic acid. Basic, by now you should know how to draw the structure of acetyl salicylic acid. In any question, nobody will give you the structure of acetyl salicylic acid or salicylic acid, so that you must know how to draw it. So the salicylates are derivatives of 2-hydroxybenzoic acid. So if you have drawn, and even if you don't draw, go to page, you don't even have to draw because it has been drawn for you. Go to page 2 and you see salicylic acid. And if you see the salicylic acid, we are calling it 2-hydroxybenzoic acid. Look, the carboxylic acid, when we do nomenclature of any compound and carboxylic group takes first priority. It is given first priority over all the other functional group. It doesn't matter whether it's an aliphatic molecule or a cyclic molecule. Whenever you have carboxylic group, it carries first priority. So for us to name that compound, that is why we are saying the carboxylic acid is in position 1, the hydroxyl group is in position 2. When now we name it, because carboxylic acid takes we look at the common name. The common name of a benzene ring attached to a carboxylic group is benzoic acid. So 2-hydroxy-benzoic acid, which is also salicylic acid. Salicylic acid was used medicinally as a sodium salt, but replaced therapeutically by the acetylated derivative acetylsalicylic acid or aspirin. Therapeutic utility is enhanced by acetylation. So if we are only saying, why was it replaced? It was, one, it had a bad taste. Salicylic acid has a bad taste. So it was acetylated to give us acetylsalicylic acid, which had a better taste and also which had lower toxicity in terms of acidity. And of course, also its activity was also enhanced by esterification, because esterification of the hydroxyl group increased the lipid solubility, and therefore that molecule could penetrate the membranes and give us some activity. So the therapeutic utility is enhanced by esterification of the phenolic hydroxyl group, as in aspirin, and by substitution of hydrophobic or lipophilic group at carbon 5 as in diflunisol. We had already looked at diflunisol, and we had said if you look at diflunisol, it has a second group. If you look at the number 1, 2, 3, 4, 5. So the second hydrophobic group, which we already have said, addition of a second hydrophobic group, which is non-coplanar, will increase in activity. This second hydrophobic group also is lipophilic, also has halogens which decrease metabolic rate, giving this compound much higher activity. But of course, we need to understand, because of the halogens, which are electron withdrawers, that drug will also have more acidity. It will have also more acidity than salicylic acid, because the halogens, are electron withdrawers, and therefore making that drug more acidic than salicylic acid. But we are saying addition of that group 1 gives us a second non-coplanar hydrophobic moiety, which corresponds with the position 11 of our arachidonic acid. It also increases the lipid solubility, and also it increases the lipid solubility and also decreases the rate of metabolism. And in doing all that, of course, increases the activity of that drug, but for sure, definitely also increases toxicity in terms of acidity. So I hope you understand that, but we'll go back to diflunisol. The salicylates are strong organic acids and salts with alkaline materials. And again, just below that, page 2, we had already said that most of the salicylates, look at that, is salicylic acid. They are strong organic acids. They can form salts with weak bases like sodium bicarbonate, and of course, sodium bicarbonate. They can form salts. That is at the carboxylic group, and the hydroxyl group can also form salts with strong bases at the hydroxyl group. So note that the carboxyl group is substantially more acidic and now necessarily at physiological pH than the phenolic group. Of course, that is why for the phenolic group to undergo ionization, you must react it with a strong base, whereas the carboxylic acid, you can react it with a weak base. And that is well demonstrated on page 2. I'm in class. I'm in class. Hello? I'm in class. This volume not low. The salicylates have potent anti-inflammatory activity with mild analgesic and antipyretic activities. These compounds are mainly COX-1 selective. They are bound with higher affinity by COX-1. Toxicity include GIT irritation, hypersensitivity reactions. They will bind the carboxylic group, will bind the albumin, inhibition of platelet aggregation, and ototoxicity or tinnitus. Of course, while we are saying inhibition of platelet aggregation, they will also bind. There is an enzyme that we said is responsible for platelet aggregation. That the enzyme, the prostacyclin synthetase, which
will synthesize prostacyclins, and therefore they will also inhibit that enzyme to a greater level than the thromboxane. Let's look at it properly. The prostacyclins are responsible. The prostacyclins are responsible for the prostacyclins are responsible. They bring about vasodilatation and inhibit platelet aggregation. The thromboxanes are responsible for increased platelet aggregation and of course vasoconstriction. So that means these drugs will also are binding the thromboxane synthetase more strongly than the prostacyclin synthetase, and therefore they will inhibit platelet aggregation. They will inhibit platelet aggregation by binding the thromboxane more potently, more strongly than the prostacyclin synthetase. The therapeutic toxic actions that in the gut can be related to the ability or to bind this. We have already mentioned. Of course, the toxicity is because they will bind the constitutive COX-1, therefore block the homeostatic effect or activity of this drug, or so not of these drugs, but of the prostaglandins. Of course, we have mentioned that the salicylates, most of them, especially acetyl salicylic acid, they have one role. They are the only example, especially acetyl salicylic acid. It is the only example of an non-steroidal anti-inflammatory that binds the COX enzyme irreversibly. Again, if you look at page 2 at the bottom, you will see there your acetyl salicylic acid, and that acetyl salicylic acid, of course, in the body, it will bind with a nucleophile. There will be a nucleophile coming in, and in binding a nucleophile, as you can see, the nucleophile is being acetylated, and of course, you release salicylic acid. So you are starting with acetyl salicylic acid in the body. You can have nucleophiles in terms of the plasma proteins. You can have a nucleophile also in terms of the enzyme itself. The COX enzyme is also a nucleophile, because these, of course, they will always bind on the nucleophilic site. So this acetyl salicylic acid can bind a nucleophile in terms of the plasma proteins, where it will bring, of course, allergenicity. It can bind a nucleophile in terms of the COX enzyme, either COX-1 or COX-2, whereby it will bring good activity or toxicity. And if you look at what happens to your nucleophile protein, consider that nucleophile protein is your enzyme. Consider that is your enzyme, either the COX-1 or the COX-2. You can see what has happened to your enzyme. It has been acetylated. That enzyme is acetylated. And once it has acetylated, that's why we talked about irreversible binding through acetylation of the nucleophilic site of the enzyme. And that's why we are saying it can bind the enzyme COX-2 in the joints. It can bind the protein in the GIT tract, or it can bind the circulating proteins. If you bind the circulating proteins, you will have allergenicity. If it binds the protein COX in GIT, it will give you gastric irritation. If it binds, of course, the COX-2 in the joints, it will give you anti-inflammatory activity. So that's what we are saying. And that binding is irreversible because it is through acetylation. And you can also note that after the acetylation, what do you release? You also release acetic acid. Of course, salicylic acid, sorry. You also release salicylic acid. The salicylic acid is also a non-steroidal anti-inflammatory drug, and that is why acetyl salicylic acid is also very effective, because it will act itself first by acetylating the proteins, for example, the COX enzyme, and in acetylating the COX enzymes, it will also release salicylic acid, and the salicylic acid also has some activity. Salicylic acid has some activity itself, so you can see it will have very, very good. The salicylates, the SAL, the simplest active compound is salicylic acid anion. So salicylic acid anion. So the carboxylic acid must be available. It must be ionized for activity. The carboxylic group is necessary. The carboxylic group is necessary for activity, and the hydroxyl group must be authored to it. So you're looking at the SAR for the salicylate. The carboxylic group needs to be there, And the hydroxyl group cannot be meta or para. It must be ortho to the carboxylic acid for non-steroidal anti-inflammatory or anti-inflammatory activity. Introduction of electronegative groups and lipophilic groups increases anti-inflammatory activity and toxicity. So if you add electronegative, remember, are groups that have higher pull. They have higher love for electrons. They will pull electrons to themselves. So they have electronegative groups will pull electrons to themselves. And of course, when you introduce these groups, and we have seen so with diflunisal, you will increase activity. More often than not, you will also increase lipid solubility, increase anti-inflammatory activity, but as I have said, increase toxicity. And I've explained why you will increase toxicity. You will increase toxicity because these electronegative groups, these groups will pull electrons to themselves. Once they pull electrons to themselves, that means the carboxylic group will be more ionized. The resultant molecule will be more ionized in aqueous media, and therefore it will be a stronger acid. The stronger the acid, of course, the stronger the gastric irritation. Therapeutic utility is enhanced by esterification of the phenolic hydroxyl group as in aspirin and by substitution of a hydrophobic lipophilic group at carbon 5 as in diflunisal. So that was just following on the earlier point, where now we are very specific. We do have examples. Now we look at the examples of these drugs. Again, I believe you have all of them somewhere. If we do have, we do have examples of this, I hope. You look where they are. Another have the salicylate, I think. Looks like I didn't give you the structures of the salicylate. Wow. Oh, looks like mine I've omitted that, the structures of the salicylate, so you can look at them and draw them quickly. I don't know whether you as you have the structures. I was hoping I had. So draw them quickly. You have not drawn them. So we are starting with, we have magnesium. So we are starting with aspirin or acetyl salicylic acid, sodium salicylate, sodium thiosalicylate, just an SH there. And then sodium thiosalicylate. Then there is choline salicylate. This is just choline. And the trimethyl, this is the trimethyl, triamino. The one is usually diamino. You can see this is triamino. It is triamino. 1, 2. Ethyl, ethyl group, or what we simply call choline. So choline has OH, CH2, CH2, and NCH33. So you can see that that is positively charged, and of course it is being complex with that negative charge there. So that is choline salicylate. Then you have magnesium salicylate, which again, as we said last time, is a complex of 2 salicylic acids. So that is carboxylic acid. That's it. So you complex 2 of them. And then salsalate. Salsalate again is of 2 salicylic acids through the oxygen. And of course, benolirate is a salicylic acid, acetyl salicylic acid plus paracetamol or acetaminophen being complex together. If you haven't drawn them, then I will be able to send them to you because of time. We need to move. So we are still on salicylates, SAL. And when you look at it as a salicylic acid, the sodium salicylates were the original product used, but required doses which had much gastric irritation and ulceration. That salicylic acid and sodium salicylate were highly acidic, and therefore they had drawbacks. Salicylic acid is their nounized form. In their nounized form also has a bad taste. Thus the sodium salt is used more frequently. So again, as I said, it has a bad taste, and therefore you derivatize it as a sodium salt. Salsalate and benolirate are prodrug esters. We have looked at that. The sodium salt is freely soluble in water and faster absorption. Salsalate is only half as potent as an analgesic or antipyretic as aspirin. but produces less GIT irritation because of the esterification. Salicylate is a diester of salicylic acid, and benzoate is esterified with acetaminophen or paracetamol. That is just stating what we've already said. But we are noting that salicylate is less potent, because when it gets into the body, for it to release the active molecule, remember the carboxylic group has been bound. For it to release the carboxylic hydrolysis, it has to undergo hydrolysis for it to release the active moiety. It has to undergo hydrolysis, and I believe that is why it is becoming less potent than salicylic acid. It is insoluble in gastric pH, but soluble in the small intestines, and that also causing less gastric problem. It is not soluble in the gastric pH, soluble in the small intestines. You know, small intestines is basic pH. The stomach is acidic, so it is insoluble in the acidic pH, soluble in the small intestines, and that causes less gastric problems, because gastric problems is within the stomach. Further, it is useful in hypersensitivity to aspirin. Hypersensitivity to aspirin is a result of acylated plasma proteins. Since it produces salicylic acid, it can be used in aspirin sensitive patients. All we are saying, because acetylsalicylic acid, they have patients, in fact, who are very sensitive to acetylsalicylic acid, because, as we said, remember, we said the aspirin, acetylsalicylic acid, can acetylate the plasma proteins, and in acetylating the plasma protein, it will trigger allergic reaction. So you can't give salicylate to such patients, because it does not produce it does not acetylate. It will just produce salicylic acid. It is a little bit more, it's mild. It has less gastric effect. It has lesser gastric effect within the stomach, so it's a little bit safer than acetylsalicylic acid in terms of GIT irritation, and also in terms of hypersensitivity. Then you have the sodium thiosalicylate, used in rheumatic fever and acute gout and so on. Magnesium salicylate, the same. Of course, all these drugs, as we have said, they'll be released. When you take them, they'll be released to form the free carboxylate ion for activity. Magnesium salicylate forms stable aqueous solutions and show some success in overcoming GIT problems. Choline salicylate is also absorbed faster than aspirin, producing higher salicylate blood levels, and an aqueous formulation is also available. But these are not some of the drugs that are commonly available. Of course, we know the one which is most available is aspirin, although, of course, it has its major disadvantages. Pharmacological actions are attributed to both the aspirin, acetylsalicylic acid, and also to salicylic acid itself, as we have said. The acetylsalicylic acid will acetylate the enzyme, well, of course, the salicylic acid will act like all the other drugs. So a salicylic acid will not acetylate, but it will inhibit the cyclooxygenase enzyme, whereas the acetylsalicylic acid will acetylate the enzyme. So there is double activity, and that is what brings about the activity of acetyl. It is highly soluble in water, absorbed as such, but is hydrolyzed rapidly to acetate and acetate by esterases. It is reversible. It reversibly inhibits the enzyme acetylating and acerine residue, thus preventing access to the cyclooxygenase site. Salicylic acid forms a reversible ionic bond with the cationic site on a cyclooxygenase. So that one acts normally, but the acetylsalicylic acid, as we have already said, will acetylate the enzymes. And this is the same thing we have said. So you have, this is acetylsalicylic acid, that is your enzyme there. This is our acerine moiety. So acetylate, so this group acetylate that. So there is breakage there. So you can see finally your enzyme is acetylated. Its serine moiety, you have release of salicylic acid. This has also been demonstrated on the sheet that I've given you. So you have your salicylic acid, which now will inhibit the COX enzyme kawaida 2, and you have also your COX enzyme inhibited irreversibly through acetylation. So that finishes the first group of the salicylate, because these are the ones we are going to go to are just slightly, very slightly different. Is there any question? Any question? As you give me a minute.